I'm going to talk to you guys about the future of circuitry and downhole tools, and that's going to be, in our mind, it's going to be something called LTCC, which is low temperature co-fired ceramics, which is a type of, I guess instead of having a polyamide substrate on your circuit board, you use this ceramic circuit board. So we're in the oil field industry, and we've got one of the challenges is that as oil gets harder to find, they're drilling deeper, which means that the oil wells are getting hotter, which means that circuit boards and current packaging technologies for use downhole aren't quite working. And our challenge is to basically make your cell phone work while you're baking a cookie. So if you bake a cookie at 350 degrees Fahrenheit for 20 minutes, oil and gas companies are expected us to have a pressure gauge that will work at 350 degrees Celsius for 3 to 4 years. And the future of that is now going up into the 400 degrees Fahrenheit or 200 degrees Celsius range. So if we take a look at our standard circuit board, it's got some polyamide base with a bunch of plastic chips, some solder. And for the last 10 to 20 years, companies like ourselves have been working really, really hard at getting this to work reliably. So right now, we've got a standard surface mount circuit board that will work at 200 degrees C. It will work at 350 degrees Fahrenheit, but its lifespan is limited. So at 200 C, we're seeing basically a month worth of use. At 300, we claim to get about a year, but still that's not good enough. People want permanent applications, they want longer reliability, and we've got all these problems like vibration, shock, all these other things that come into play. Oh, should just play here. I've got a little animation. There we go. So to work through the challenges of trying to get this thing to work hot, we have to figure out where the root cause of the failure is. And what I'm going to do is blow down and look at the chip itself, because the chip is usually what most of our IP is looking at. We're trying to find new chips that work hot, and I want to explain how a chip is basically made. So when you go and make a chip, you basically start with a piece of aluminum and you punch it out and you get the base, right? Then the manufacturers take a bit of epoxy, they dab it down in the middle. Then they'll take the actual die, which is the real brains of the chip, and stick it on. Finally, they're going to wire bond the die out to the aluminum pads, basically like stitching it. It's a weld. And the last step is to put a bunch of plastic on the outside of the chip. And this is our problem. The whole assembly, but primarily the plastic. Plastic melts. If you consider all the different coefficients of thermal expansions, we've got plastic, which expands quite rapidly. We've got aluminum, which expands at a different rate. And we've got these little tiny wire bonds connecting the two to the die. And obviously, you start heating them up, you get a breakage. As well, there's moisture inside the package. The guys that manufacture these chips, they don't really care about us. They care more about cell phone makers. So as you heat it up, there's a big possibility that there's going to be cracks, expansions. So what we're trying to do is take the die out of the chip and put it onto its own substrate, repackage it, change the metallization schemes so that you get a longer lasting metal joints. And if you look at the final structure, you've got no more plastic, you've got a ceramic substrate, you've got raw die, all the parts are smaller, so when you think about the shock and vibration, the mass downhole, right? Everything lasts longer. Everything's more dynamic. Another big effort is size reduction. So if you think about the area, we can reduce the size of a circuit board by up to 80% by going to the new technology of LTCC, what we call a hybrid as the final structure. So with this, we're expecting to get about 100 times the reliability of current surface mount technologies downhole. That being said, when we take our 30 days, we can now get 3,000 days. Yeah, that's the end of my presentation. Actually, that was really quick.